want to show you all or give you a short introduction how we are using our data and knowledge in-house to support our customer, identifying the potentials to save money and also CO2 emissions, and to find the optimized configuration, the optimized assets for the track, and considering also the boundary conditions. But before I starting the presentation, may I only want to say three sentences about my person. As they mentioned already, my name is Petra Wilfling. I'm working at Voestalpine since 2020, and here I am responsible for the LCC calculations for turnouts. Before I started at Voestalpine, I had the honor to work with Peter and Stefan at the Institute of Railway Engineering and Transport Economy. And there I have to say I learned all about this topic. So it's a pleasure for me to work with the same topic now at Voestalpine and to show you today what we are doing and how we can help our customers. So the purpose is, as I told you before, we want to support our customers in making strategic decisions regarding new investment, replacement investments, so only for single assets, for example, also regarding the time for replacement and the service life for assets. Here we try to find, or we, together with our customer, we support them to find the optimized configuration, the optimized investment for his boundary condition and the parameters. To be able to do this, we have developed, or we are still developing, our LCC Track tool. The tool is combined of our former two tools. So before our LCC Track was born, we had two separate tools, the LCC Rail and the LCC Turnout. Those two are the basic, and with a completely new structure and additional features, our LCC Track was born, which was developed or showed at the InnoTrans the first time. Our new tool has a lot of new features. Now we are able, for example, to calculate entire infrastructure networks, including turnouts and the rails. Before that, we were only able to calculate or to compare turnouts and track sections separately. This is also still possible in our new tool, but we can also combine those calculations. And we are able to calculate different network strategies. So we have the opportunity at least to combine 6 strategies for the infrastructure network or for the asset to do the LCC calculation. As the climate change doesn't stop, we have also implemented the environmental effect, because we believe that the customer should know before installing the infrastructure network, that he should know how much emission he could save, or how he can, for example, protect the environment. We have also implemented interactive report. This is completely new, because now the customer has the opportunity to get a web-based formula, so a web-based link. Here he can go directly into the calculations, into the report. He can see the results in different ways, the different figures are calculated, and he, for example, sees also the figures and the costs, for example, for each single asset, but also for the entire project. To show you the tool today, I brought an example with me, and so no, yes, here it's come. This example is a demonstration tool to show how the tool is working, how the data is getting out, or how the data is used. Here, for example, you see the production factory in Donawitz, so where the rails are produced. And on the left-hand side, you see the project scope, so really the entire network of the production site. Our tool is using OpenStreetMap to get the data of the whole infrastructure network. After validation, the tool is calculating the radii out of this information. And like you see here, we have also the information due to the OpenStreetMap for each turnout. And this turnout positions can then be additionally filled with the information of the radii and the information of the turnout type, for example. How we can support our customer, we are calculating or we compare different strategies. That mean in this case, we have 3 examples chosen or 3 strategies chosen to show you how the tool is calculating. So we define the different strategy with our customer, what would be possible to use, and then to show the differences of those strategies. For this example, we have chosen the basic configuration for the rail network. It means that we're using the R260 rail grade, and for the entire turnouts, we are using turnouts with concrete sleepers, standard switch rail, build-up crossing, and also with the R260 rail grade. The second strategy is the industry standard. Here we have for the track network combined strategy of rail grade. Here we are using R350 HD for radii below 1000 meter. And for the other radii or straight track, we are still using R260 rail grade. And for the turnouts, we're also using the rail grade R350 HD, load capacity optimized or a kinematic gauge optimized switch rail, and the cast manganese crossing. And the last strategy for this example today, we designed the state-of-the-art. Here we are using, instead of the R350 HD, the R400 HD rail grade below 1000 meter. And for turnouts, we are using also under sleeper beds, and the cast manganese crossing is explosion deep hearted. To compare those strategy, of course, it's necessary that the tool have a database behind. So behind the interface, we have a database for track and for turnout. For track, we have a table of wear in relation to radii and the steel grade, so like you can see below. There's also an algorithm for deterioration behind all the interface, and the wheel limits for rail exchange, or for example for grinding and milling, are specially designed or specially chosen for each customer, so regarding their interactive boundaries. And of course, we couldn't calculate life cycle costs if we do not have costs behind them. So we have also stored costs for maintenance and investment, and of course the CO2 values. For turnouts, we have in our database, we have the service life of the configuration of the turnouts, including all maintenance tasks, like the table showed, like Stefan showed us before. Of course, here we have stored and saved the costs for maintenance and investment that the tool is able to calculate the figures, and also CO2 values for the production, for the transport, and the maintenance task. With those database, or with this database behind, the tool calculates different values, so the annual costs or annuities, the capital values or amortization time. But I brought today only the the slides from the annuities show from the annual costs with me to hold it a little bit shorter. For example, here you see the basis configuration. The turnouts are marked red and orange. That means these turnouts have higher annual costs. This is lead back to the higher maintenance demands, to the shorter service life, and the higher wear in the small turnout geometries. The industry standard, here you see it's better. So we have reduced annual costs. The turnouts have, due to the different rail grade, due to the different configuration, a longer service life and reduced maintenance needs. And here, for example, the customer could save 16% from the annual costs. And by using the state-of-the-art strategy, so with undersleeper beds and explosion deep hardened crossing, you see all turnouts are marked in light green. So here we have, at least for the whole project of the whole strategy, or for all strategies, the lowest annual costs due to the longer service life and lowest maintenance. At least here with this strategy, 25% of the annual costs can be saved. Regarding the track line, we have a similar picture here. You see in the smaller radii, we will have higher annual costs. This is also lead back to that we are using here for this strategy the R360 railgrade. This railgrade has a lower rear resistance, so a higher maintenance is needed, and also replacements are needed more often. With the industry standard, so with the combination of the R350 and R260 railgrade, we can save 28% of the annual costs. And by using the state-of-the-art strategy, that means in concrete in 400 HD railgrade below 1000 meter, you can save 43% of the annual costs. But to find the perfect or the best configuration, it doesn't have only influence on the annual costs. As I told before, we also have implemented CO2 emissions. It's not surprising if we have to produce new turnouts, or if we have to produce rails, we emit CO2 in the atmosphere. So we can also here illustrate our CO2 emissions for this strategy. For example, here you see the basis configuration have turnouts marked in red, so higher CO2 emissions comparing to the others. If we are using industry standard, you see the turnouts over the entire production site will be marked in green and orange, so we can save CO2 emissions, in special here 11%. And by using the state-of-the-art, we can save 23% of CO2 emission. Oh, sorry, that was one too much. So we are calculating different strategies to show our customer how the decision of the configuration of the turnout configuration and the choice of the rail cans influence or have effect on the CO2 emissions and also on the annuities. So by reducing maintenance needs with an extension of service life, it is possible to reduce annual costs here, for example, for the whole project, 28%, and also for 38%, you can save this amount for CO2 emissions only by choosing the optimized configuration of material and design. also with a consideration of the boundary conditions. And to give an easier feeling for the 38% for CO2 emissions, that's 560 tons. And this is the same amount what 7,025 trees can compensate within 1 year. So that's the amount of CO2 emission can be saved. So that's the short introduction of my side. Thanks.